Welcome back to ECE 442-542. I'm just checking in. This is the summary of our office hours that were held yesterday. We're in the spring of 2020, and I just wanted to make sure that everybody was following along, and I'm trying to make these summaries quick but hopefully helpful, and I will stay in touch. Here are the questions that were really raised, and if you want to resubmit your homework, please feel free to do that. You can upload a new homework, just put it all into one PDF, the new one separate from the old one, and just say grade the most recent in the assignments folder, and that should be acceptable. Let me quickly start by trying to summarize the questions that were raised during office hours, and these are concerning homework number 4 that has been modified in terms of its due date. It's now due tomorrow on Wednesday. So these are all dealing with, when I refer to a problem, it's relative to homework number 4. The first problem is the phi matrix in this zero order hold equivalent, which is equal to e to the capital A t, where t is the sample period, that messy? The short answer is yes. Phi is computable by hand by doing this inverse Laplace transform of SI minus A inverse and evaluating that at t equal to capital T, where capital T is the sample period. The second question, which has a few parts, can we use MATLAB to actually find that state space zero order hold equivalent? And the answer is yes. C to D can do that. You would just, in the first argument of the C to D function, need to represent that as a continuous time state space representation, which here I'm calling SYS underscore C. The second argument is the sample period T, and we'll talk a little bit about what's reasonable there. And the third argument is the method, which you want in single quotes to be, in this case, ZOH, or the zero order hold equivalent. A follow-on to that, can this C to D function in MATLAB be used for other discrete equivalents? Quickly, yes. It depends on the method that's used or placed in that third argument. You can have the zero order hold, which is scenario number 2 that we've talked about, or MATLAB does do the trapezoidal. They just refer to it as the Tustin. You might hear that in other sources called the bilinear, but in MATLAB it's called the Tustin, and it will do the pole zero mapping, and you do that in homework number 4, and there is a difference, and we'll talk a little bit about that, but there the method would be matched inside the single quotes. Why are there different methods? It depends on the circumstance, and we talked about that in lecture 4.1. We have 2 different scenarios. Scenario number 2 is what we really started with, and that's the zero order hold equivalent. Scenario number 1 in these discrete equivalents deals with the numerical integration equivalents, which are the forward, backward, and bilinear, and it also concerns the pole zero mapping strategy. And we'll talk more about those in the answers. Does T seem reasonable? That's asked of you in several of these questions on the homework. Remember that the sampling frequency that we're using in this class, since we're dealing in a control scenario, is 2 pi over capital T. T is our sample period, but we now, rule of thumb, say let's make that 30 times the highest frequency in our system, omega sub h. And omega sub h, if you're not trying to modify the speed or the dynamics of your system, that may be the highest frequency in your original transfer function, if you are modifying the dynamics or the speed of the system, then omega sub h may be what you desire to achieve, and that will then influence how fast you sample or what you select for capital T, which is related to the sampling frequency omega sub s. And the last problem that we'll talk about deals with homework set number 4, problem 4, which how do we perform pole zero mapping when we have complex factors? And this relationship that we know, z is equal to e to the st, still applies. Let's go through some answers, and here I've simply cooked up an artificial system. Here's a second order differential equation. You can translate that into a block diagram. Here it's an all-integrator block diagram, and the strategy for finding a state space representation is to label the outputs of these integrators as your state variables. Then the inputs of those integrators are actually the derivatives of those state variables. And that's really how you can now find your state space representation for a continuous time system. And I will assume then that you can relate the particular variables in these matrices to how they arise in this block diagram, which follows from this second order differential equation in terms of y. This block diagram gives us a way of interrelating the input to the output, and we can now write that or represent that in a state space representation. And state space representations are not unique. It depends on how you've labeled your integrators in your block diagram or how you even created your block diagram. Here, this is consistent with that all-integrator block diagram, and I will use A, B, and C throughout this discussion or through these answers. How do we find the zero order hold equivalent? And remember, this is scenario number 2 that we talked about in lecture 4.1. This is when you have a zero order hold preceding your system's transfer function, and you're trying to now incorporate the dynamics of the zero order hold along with the plant to obtain your discrete equivalent. Here, the system matrix phi is e to the at. The input matrix gamma is found by using that matrix exponential e to the a mu times the continuous time input matrix B and integrating that over one period from 0 to capital T. E to the a capital T is found from e to the a little t by replacing little t with capital T. And to do that, or to find an expression for this matrix exponential e to the a little t, you can actually do that by inverse Laplace transforming this matrix Si minus A inverse. Why is that? Well, suppose that we had, this is a homogeneous dynamical system. We don't have a forcing function, but it sort of illustrates how we can find that state transition matrix e to the at. That's maybe a new phrase for that, but that's what e to the at is. It's a state transition matrix. We can now Laplace transform that and keep track of the initial conditions. Remember, little z is a vector, potentially. Capital Z is also a vector, but it's capitalized to denote that it's now the Laplace transform of the vector, time vector, little z of t. We now can introduce this placeholder, this identity matrix, collect the capital Z of S terms on the left-hand side, move the initial condition on the right-hand side. We can solve for the Laplace transformed state vector, capital Z of S, by multiplying both sides through by Zi minus A inverse. That's in the frequency domain. We can put it into the time domain by inverse Laplace transforming, and that's where the e to the at matrix comes from, or that's the state transition matrix. That's why e to the at does correspond to this inverse Laplace transform of Si minus A inverse matrix. In our example that we started with here, these aren't the numbers for problem 2 in homework set number 4. Remember, this is office hours and I'm trying to give you some representative concepts. Let's just walk through that. We can now find the inverse of that 2 by 2 matrix by dividing by the determinant 1 over, now this is the product of the diagonal minus the product of the off diagonal. And in a 2 by 2 case, we can simply interchange the diagonal entries and negate the signs of the off diagonal entries. We can push that scalar denominator into all 4 terms, and we now have this 2 by 2 matrix that is the Si minus A inverse matrix. And we have 4 different transfer functions, and we have to then inverse Laplace transform each of those in order to find the appropriate expression in each of the 4 entries in that 2 by 2 matrix. If we simply look at the alpha sub 2 of t, and you would have to do this for all 4, that's why I said it's a little messy, but let's now look at what we could do if we wanted to inverse Laplace transform that lower right hand element, or the alpha sub 2 entry. We can actually complete the square in the denominator. I've set this up to be clean, and that now gives us an s plus 2 quantity squared plus a 4 quantity squared. And if you're familiar with that notation, that's now the distance we are into the left half plane from the imaginary axis. That's the sigma. And the damped frequency of oscillation is given by omega sub d. Again, this is in the s plane. Well, we don't see immediately that this expression inside the curly braces looks like a damped exponentially damped cosine or an exponentially damped sine. It's actually a combination of those, and that's what I'm trying to illustrate here. Here I'm saying, oh, here is our exponentially damped cosine, and here is our exponentially damped sine, and we have some linear combination of those. We have s plus 4 in the numerator, and that must be some linear combination of s plus 2 and 4. And what linear combination that is will determine the values for a sub 1 and b sub 1. If we didn't have to find those or evaluate for alpha 1 and b1, we could simply write down the structure of our entry in the 2-2 entry of that inverse Laplace Si minus A inverse matrix. Remember, this is the alpha sub 2 of t entry. We could find A1 and B1 by equating the numerators. We're trying to make now this numerical expression equal that numerical expression. Or we're setting s plus 4 equal to A1 times s plus 2 plus B1 times 4. Distribute the A1, equate coefficients. The S1 coefficient is 1 on the left-hand side. It's A1 on the right-hand side. That gives us A1. The constant coefficient, or the coefficients associated with z raised to the power 0, on the left is 4. On the right, it's 2A1 plus 4B1. We already know A1, that's 1. So we can solve for B1, and now we have the A1 and the B1. Again, that's one of the 4 entries. Moving on now to question 2, which was using MATLAB to find this zero-order hold equivalent of a state space representation. Here it could be a command. Obviously, you would need to precede this command with the commands necessary to produce this object, which is a state space representation, and I've tried to illustrate that below. But if you were actually doing this, you would actually need to do these commands sort of from the bottom up before you introduced this C to D command. We've defined then a state space object with the A matrix, which I'm saying is lowercase a, it's 2 by 2. The lowercase b is 0, 10, stacked on top of each other. C is 1, 0, written side by side, that's a 1 by 2, and D is a 0. Then the second argument in C to D would be the sample period, and the third argument in C to D in single quotes is the method that you're trying to use to produce the continuous to discrete transformation. Here it's the zero-order hold. If, in fact, you could get more efficient, and for the zero-order hold, that's the default in MATLAB, you could present C to D with 2 arguments, and it would give you this SYS underscore D as the zero-order hold equivalent. That's the default. And here, then, this SYS underscore D would produce this object that contains the system matrix phi and the discrete time representation, the input matrix gamma, the output matrix C, and the direct feed-through matrix J. Other methods can be used with C to D. Suppose we wanted to do, and now we're doing a discrete equivalent for scenario number 1, which is we're just trying to get a direct equivalent of the transfer function C of Z to C of S with C of Z. Suppose we now define that transfer function in MATLAB. We call it C underscore 1. Let's say that's our first transfer function. It's transfer function comma 10. There's the numerator. And then the denominator is written as a polynomial to account for the coefficient preceding the 1. That's the 1. And then the constant coefficient is the next argument or element in that row vector, and that's 10. We now can find C underscore 1D, or the discrete equivalent, using, let's say, the trapezoidal strategy, which in MATLAB is the method Tustin in single quotes. We now just need a sample period, capital T, and what would be a reasonable T? Well, again, we said we want, for our purposes, that to be 30 times omega sub h, or t to correspond to that. Remember, omega sub s is 2 pi over capital T. The highest frequency in this transfer function, we're not changing it, we're not speeding it up. There's a pole at minus 10, so our highest frequency is 10 radians per second. We take 30 of those, and that's omega sub s. That's 300, and we set that equal to omega sub s expressed in as a function of capital T, which is 2 pi over T. We solve that for capital T, and we end up with 0.02 seconds. If we now put that in for T, 0.02, and we already now have defined C underscore 1, the continuous time transfer function, and apply the method Tustin, we would then, MATLAB would produce this first order transfer function for the discrete equivalent of that low pass filter. Here it's a discrete time low pass filter with a sampling period of 0.02. Why are there different methods? Again, we have scenario number 1 where you're simply trying to, and I don't know why I put that as a D, this should be a C. C of Z. We're trying to now find an equivalent to this continuous time transfer function in the discrete time setting, and this could be done for the forward, backward, and bilinear or trapezoidal or Tustin numerical integration strategies, or it could be used for the pole zero mapping. That's scenario number 1. And second scenario is scenario number 2, which is when you have this, and hopefully you can see the slight difference between blue and black here, continuous time to discrete, and the blue and black here. In the continuous time, now we are actually trying to incorporate the zero order hold dynamics along with the system transfer function g of s in order to obtain the zero order hold equivalent capital G of z. So which of these methods or strategies you apply, and remember, MATLAB really doesn't do the forward and the backward. It does the Tustin, it does the pole zero mapping called matching or matched. We'll try to find that maybe in a minute, maybe not. In MATLAB, actually I can do that right now. Matched is what they refer to it or call it in MATLAB. And then it has the scenario number 2, which is the zero order hold. Does the sample period seem reasonable? Well, we just talked about it in answer 2b above. Let's now go on into question number 4, which dealt with problem 4, and that will also address a reasonable value of t. And this is where we're mapping complex factors. Again, we still focus on this relationship between s and z. Suppose somebody says, oh, I have complex conjugate poles. I'll just look at the top one. I have a complex pole at -3 plus j4. What is a reasonable sample period for that? And here I'm putting this sample period in with this complex factor mapping. So this is just an intermediate step in mapping from C to D, or using the pole zero mapping approach. What is reasonable? Here we have a real part of 3, or a horizontal leg of this triangle. We have a side of 4 for the vertical, and the hypotenuse. This is a 3, 4, 5 triangle. The hypotenuse is 5. That's now our highest frequency that we're interested in. So now we have 30 times 5, that gives us 150 radians per second. We set 150 equal to 2 pi over t and solve for t. We're approximating pi to be 3. And so now a reasonable sample period for this particular example would be 0.04 seconds. If that's the case, now let's go ahead and map these complex poles at -3 plus and minus j4 into the z-plane. And let's just look at one at a time. Here's the pole in the second quadrant of the complex s-plane being mapped into a particular location in the z-plane through this e to the st relationship between z and s. So we have e to the -3 capital T times e to the j 4t, and that's just using the property of exponents. We have an e to the j, but that now just gives us e to the j angle. In this case, the angle is radians. If we want it in degrees, we can convert that through this scaling factor of 180 over pi. So we now have an angle of about 9 degrees, and we have a magnitude of z equaling e to the minus 0.12. So here is our r, and here is our e to the j theta sub d. We could write that in a phasor form, which you're probably familiar with, but that's really just equivalent to 0.8869 e to the j 9 degrees. We can use Euler to take that into rectangular form, and now that we know where the positive imaginary component pole mapped to, we know where the conjugate is. We just negate the sign of our conjugate variable. Now we have z1 and z2. We can multiply those two factors. We have z minus z1, so there's one pole factor. Z minus z sub 2, that's a second pole factor. If we multiply those together and realize that we can maybe clean this up a little bit by simply partitioning those two factors appropriately, we can see that what I have now in square brackets is the quantity z minus 0.8756 squared. We then, the cross terms cancel because we have a minus sign here and a plus sign there. This minus sign comes down there. Here's one j and here's another j. And we now have a minus, or we end up with the original squared factor plus the imaginary component of that set of complex conjugate poles squared. Its imaginary component. So now once you have this pole this pole location in rectangular form, you can immediately write it in this quadratic structure, and you can hopefully now see that, oh, we have a real part of 0.8756 and our imaginary part is 0.1413. So if we now had a transfer function that had the original S domain poles at -3 plus and minus j4, how many zeros at infinity does that C of S have? Hopefully now you know that that's 2. We have a constant numerator and we have 2 poles in the denominator, so we have a pole zero excess of 2. We have 2 zeros at infinity. I'm going to call that I sub z. We now want to translate that, and I'm not sure why, I guess I'm doing my alphabet, but we really want this to now be the discrete equivalent of C of S. So this is now C of z. We know where those complex poles go in S. We've converted those now into where they belong in the z-plane. What we now need to do is figure out what goes in the numerator of this discrete equivalent. It's going to be some gain, but we now map, our default, we map so many z plus 1 factors. Those correspond to the number of zeros at infinity. In our case, we had 2 in this example, so we would include in our numerator k times z plus 1 quantity squared. The denominator stays the same, and we would find k by matching the gains of C of z and C of S at some logical value. In this case, this is a low-pass filter structure, so we would probably map or match the gains at low frequency, or DC. MATLAB by default actually reduces the power of that factor z plus 1 by 1. So if you're now looking at what MATLAB gives you with this matched C to D function, it's going to give you a different numerator polynomial. It's going to be z plus 1 in this example, not z plus 1 quantity squared. And if they match the gains at the same frequency, their gain, k bar, is not going to be the same as your k, because in ours, if we matched it at DC, then z is equal to 1. Now we would have 2 quantity squared, or 4, scaling k, along with the denominator. And MATLAB would have 2 raised to the first power, scaling their gain, k bar. And then again, the denominators in both would be the same. But we would find their RK and MATLAB's k bar by matching the gains. Hopefully that now provides you with a quick summary of what we talked about yesterday during office hours, and I hope that's helpful.